the coming Monday has been declared by the Institute as to follow the Friday's timetable. So Monday we will have a class at the same time. So I don't want you to think that the Monday class is off. This is following Friday timetable. So we'll meet at 10 o'clock on Monday, the same room. We continue with the we're looking at the gradient operator, how to express it in the cylindrical coordinates. For that, we look at the gradient in the rectilinear or rectangular coordinates, which is I have E1 expressed in terms of ERC. I've already got this. E2 and E3 is given by EZC. So we have this formula. So already all we have to do is substitute this here. Now we need expressions for the operators d by dx1, d by dx2, and possibly better to write this as writing it as an operation. Better to write it like this. We can operate on a function phi, let us say, a scalar at phi, psi, right? So when this is operating on psi and it's expressed like this, the psi needs to be expressed as a function of x1, x2 and x3. That's what we have considered all along. However, if I want this to act on the same function, psi, but now I have to regard this as being expressed as a function of RC, phi and ZC. Right? So I want the corresponding operation in the cylindrical coordinates. So that is the whole purpose. So E1 I just substitute here, E2 I substitute here, E3 I substitute here, and as we saw, d by dx1, okay, so it can be written as drc by dx1, d by drc plus d phi by dx1, d by d phi plus dzc by dx1, d by dzc. So this is the operation d by dx1. But now with psi, regard it as a function of rc, phi and zc, which in turn can be expressed, as we have already seen, in terms of x1, x2 and x3. So this is the formula. And so this leads to the following formula: cos phi d by drc minus sin phi by rc d by d phi, as we saw yesterday. Similarly, I can write d by dx2 or show it to be equal to sin phi d by drc plus cos phi by rc d by d phi. And finally, d by dx3 is simply equal to d by dzc. So those two coordinates are identical to each other. So now I have to substitute. So let's do the process of substitution properly and see what happens. So I have ERC cos phi minus E phi sin phi. I have to multiply this by the operation d by dx, which is cos phi d by drc minus sin phi by rc d by d phi. And then I have d by dx2 e2, right? So phi. And that multiplies this operation which I have here, sin phi d by drc plus cos phi by rc d by d phi. And then finally, I have my E3, which is nothing but EZC and d by dz. So you can clearly see, if I want to look at all the operations involving d by drc, so what will be the coefficient of d by drc? Right? So I can easily by inspection, so write it down again. ERC cos squared phi, and then I have ERC sin squared phi. So that will simply be ERC. And then minus E phi sin phi cos phi d by drc plus E phi cos phi sin phi. So that would cancel. So in effect, these two terms would cancel. And that's all I will get. Right? And then plus E phi. Let's look at what we get for d by d phi. Right? So for d by d phi, I'm getting here. Okay, this is a term coming from here, ERC minus cos phi sin phi by RC, and then ERC plus sin phi cos phi by ERC. So that would cancel, so there will be nothing coming from ERC. Even though terms are there, so there is no need that the term multiplying d by d phi should not be dependent on ERC. There is nothing like that. But you can clearly see that if you look at the terms connected with ERC, as a coefficient for the operation d by d phi, we said that the coefficient is cos phi times minus sin phi by rc. Right? And then here it is sin phi cos phi by rc. So they cancel each other. Right? And so then you look at the other term that is coming out from E phi. Right? So that is plus sin squared phi by rc. And then I have plus cos squared phi by rc, so that would simply be 1 over rc d phi d by d phi. And then I'm left with this. This is in fact the gradient operator in the cylindrical coordinates. Right? So, removing all the gaps, I simply have d by drc plus. So it has three components, just as the gradient operator is it's a vector operator. Right? So it has three components, but it's a differential operator. So the component of E1 has d by dx1. Similarly, very similar to this component for d by drc. Right? Or the component of ERC has d by drc. Component of E phi has 1 over rc d by d phi. So you can see this is dimensionally homogeneous, and that is why whenever you have the derivative with respect to phi, you are getting the rc. The length has to be there. Right? Because the gradient, that is what it is in the Cartesian, and that's reflected in the cylindrical also. The phi doesn't have any length dimension, so we immediately get the rc, and then we say c d by. So this can act. Now, the action of the gradient operator, the simplest is when it's acting on a scalar. When it's acting on a scalar, which means the scalar is expressed as a function of rc, phi and zc. All I have to do is to simply put this here. That's the operation of the gradient. acting on a scalar function of the cylindrical coordinate. Are there any questions? So the derivation is, this will be a basic. Now from this is a very critical step to get the gradient operator. Similarly, the gradient operator is spherical. Because you can see that from this we are going to get the divergence of a vector field. We've already got the gradient of a scalar. And we get the gradient of a vector field, which is a tensor actually. Then we get the divergence of a tensor. Right? If you look at the equations of motion, so the linearly viscous fluid, you get the Laplacian of the vector that will also have to be derived from this. Laplacian of a scalar is very easy to obtain. The Laplacian of a vector is much more involved. You see how to get that. So this is the simplest. Once we have got the gradient operator separately, its action on a scalar is very straightforward. Now, how would its action on a vector be? I can consider at least, I can recall at least 3 operations of the gradient operator on a vector. One is the divergence of velocity, can be any vector actually, right? So I just take this as B, and then I can now look at the curl of a vector, which is a vector. So this leads to a scalar. This leads to a vector. And then we have the gradient of a vector, which gives rise to a tensor. We now see one after another how to handle this. Once you understand the principle involved, it's very easy to actually even generalize this to, for instance, the divergence of a tensor. So we first consider the action of the gradient operator on vectors. Now, a divergence of a vector, so I will have to simply write that ERC d by dRc plus E phi by RC d by d phi is EZC. That is now dotted with. Now I have to write the velocity also in the cylindrical coordinate, in terms of its components in the cylindrical coordinate system. So that would be ERC plus E phi. If you know how to handle one term, you know how to handle all terms, not only in this, but also in all the rest of them. Only the nature of the vector operations is different. Let me take just one term here and explain how this is to be executed. That's what we are interested now. So d by dRc dotted with, we'll just take one term. So here you have, this is a this is a dot product, right? It involves a derivative and it also involves the vector. So the dot product is of this vector with this. The derivative is of this group of terms, which also includes the vector, because even though in this particular case there is no dependence on RC of any of the unit vectors, you will get it when we get take derivative with respect to phi. So how is this to be regarded? So the best way is you separate out the vector operation and then perform the derivative operation first, right? So this is to be regarded as equivalent to ERC dotted with d by dRc of dRc. Now I will have to do the derivative as I would do a normal derivative, right? Which involves, one of the terms involves a vector, so we have to be careful here. So then this would be ERC. First I will perform the derivative. So this is just using the product rule. So this would be VRC, DERC by DRC. Plus dVRC by dRC, ERC. Now I know that dERC by dRC is 0. Right? So all I am getting is ERC dotted with this. And so now this is ERC dotted with a scalar multiplying ERC. Clearly the scalar can be taken out. A dotted with alpha B, simply alpha times A dotted with B, right? So that is now simply going to give me ERC by ERC. So the operations for the cylindrical coordinates in this case are going to be considerably simplified, because for both of these two operations, so the gradient operator has three parts. For two of the parts involving the derivative with respect to RC and ZC, they will be considerably simplified because none of the unit vectors depend on either RC or ZC, right? If I now look at this and look at what will be other two terms coming out of this, so ERC, E by DRC dotted with this plus this, what would that give? Dotted, once you have taken the dot product also, it's going to give 0 because there is nothing that's going to come out of derivative. So I can simply, but what I will get, for instance, if I were to write ERC, E by DRC dotted with E phi, so I look at this, so I know that E phi doesn't depend on RC, right? So I am going to get only one term, and that term will involve E phi. So this is nothing but ERC dotted with dV phi by DRC. That is of course not 0, neither is this 0. But however, since ERC dotted with E phi is 0, this term will give 0. So initially, though it might be convenient or better, you are advised to write it out, but you can see by inspection, once I have seen that what is the basis of this is that the unit vectors are independent of RC, so I can immediately see here the only term that is going to come is the term involving the derivative of d phi. I don't have to consider the derivative of E phi with respect to RC or EZC with respect to RC, because those terms will be 0, right? But then I also see that there is a dot product waiting to be acted, and so all the dot product is with respect to ERC for the first term. The ERC dotted with E phi is 0, ERC dotted with EZC is 0. We are not going to get any more terms by the action of ERC by D by DRC dotted with the vector. Now the situation with respect to, so the only term that we are going to get is this. So I can now collect the terms and write this first. We are going to get more terms. So let's now look at what would be E phi by RC, D by D phi. Let's take this, right? So same policy, same approach holds. E phi by RC. Now D by D phi. So I use the derivative first. BRC. So I take the second operation and the first term. So clearly here we have to be a little bit more careful, because we know that DERC by D phi is not 0. However, so we have to consider that, right? So then is then equal to E phi by RC dotted. So I will be reading that would be BRC. DERC by D phi, we have clearly seen that is equal to E phi, right? Plus, we will get DBRC by D phi, but that is multiplied by ERC. Now the dot product of E phi with ERC is 0, so that term will not contribute, but I will get a contribution from this term. You have to understand that this term is coming out of the derivative of ERC with respect to phi. So if you ignore that, you will miss this term completely, right? So that is what you have to understand. Even though on the face of it, it looks like E phi dot ERC, is 0. But however, because the derivative of DERC by D phi is E phi, you are getting a term. So you cannot just neglect this term completely. So this is 0. The dot product this. So what I am getting out of this is VRC by RC. Now if I look at the second term, they also we will get a term, but that term now will not involve the derivative, because the derivative of V5 term will give rise to ERC, and E5 dot ERC will be 0. So again, writing this out, dV5 by dV5 E5 plus V5 dE5 by dV5, that is not 0, but that is equal to minus ERC, right? But then E5 dotted with ERC is 0, so I am going to get one term again. E5 dotted with E5 is 1, so I am going to get plus 1 over RC. Now we see here VZC is very easy to do by inspection. So this is, so there is no dependence of EZC on phi, right? So it will only give dVZC by d5, but then I have E5 dotted with EZC, that is 0. So clearly this is equal to 0. So I won't get any more term. We have to see, I am looking at this acting on this, right? There is no other way than to look at each term, individually, and then as you go along, you can easily convince yourself by inspection that that will be 0, right? So what I am trying to point out here is, you're having the derivative, it's acting on this product, right? But EZC is independent of phi, so you're going to get only one term out of the derivative of the product, right? So you get dVZC by d5. But then E5 dotted to EZC is 0, so that would be 0. Actually, you won't get any more terms out of this. Now let's look at the last one, right? So the last one, EZC, clearly there's no dependence on ZC of any of the unit vectors, so I can directly look at EZC dot ERC times dVRC by dZC. That need not be 0. Right? First term would involve EZC dotted with ERC. Second term would involve EZC dotted with E5. That's also 0. The third term, of course, would involve EZC dotted with EZC. That will not be 0. So that would get plus EZC. This is all you will get. Are there any questions? So the main principle is in being able to decouple the vector operation from the differential operation. So carry out the differential operation first on what is on the right hand side, or what is to be acted upon, and then let the vector act. The result dot product and cross product or tensor product, the principle, as we will now see, will remain the same. Right? So let's now do the next one, which will be the cross product of. So the experience of what we have done for the divergence, you can easily, see which are the terms that are going to contribute. For instance, let's just take ERC, D by ERC. Cross product of V. Right? So cross product, so we know that, right, I don't have to consider any of the terms coming out of the derivatives of the unit vectors, because the derivatives of the unit vectors, the derivative operation for this is d by dRc, right? And so none of the unit vectors are dependent on RC, so that none of those terms are going to come into the picture. When I do the derivative of the product, BRC then BRC. So all I have to consider is BRC, d by DRC of BRC, d by DRC of B5, and d by DRC of BZC. Those are the only terms that are going to come out of the differentiation. Right? However, the vector operation now is different because it's a cross product. So which of the terms would contribute? Would I get anything out of yes or no? No, because ERC now cross ERC is 0, right? So this would be 0, right? So I can easily write out by inspection the first set of terms, right? But now you have to remember that each is a vector. So you have to remember that to put that vector in. So the next one would be ERC cross E5, and that I know is EZC. So that would involve EZC. What is the coefficient that would multiply? It would be B5 by ERC. Whereas the next one is ERC cross with EZC. Right? That is what? What is ERC cross EZC? Minus E5. Right? So that would be minus E5. And the coefficient that would multiply is dBZC divided, the derivative of BZC with respect to RC. Right, so now the next terms, certainly these are the import this with this and this with this is going to be the somewhat complicated because I now see that E5 by RC. So I have got rid of the operation of the first two terms is contributing one component to EZC and one term to E5, right? So the next one, E5 by RC, E by E5, cross product, ERC, ERC. So how would we do it? Yeah, so who would want to come to the board and do it? Khalid, want to come to the board? No. You're going to involve differentiation, that's all. So I give you the first step also. This is the first step. From here on, it's fairly. So this you have to recognize. So once you recognize this, the same procedure we did for the dot product. Separate out the vector operation. Here it's a cross product, right? And then differentiate. Differentiation is just product 2. Put ERC plus BRC. Yes, what is DERC by D5? It is E5, right? That's not 0. That is E5. Right? So I'll write down the derivative terms also. DERC by D5 is equal to E5 and DE5 by D5. We just write it by, maybe the questions are not here, unfortunately, is this. Right? So that is not 0, but it is E5. So E5 by RC cross product, yes. Yes, so now completed. What is the cross product of E5 with ERC? Minus EZC, right? So you get minus EZC times what is the coefficient? Yeah, we take that. You have 1 over RC minus, yeah, so you, yeah, write it in the two terms here, right? You have E phi cross ERC, they've already given you the answer, it's minus EZC. What is the coefficient that will multiply? 1 by RC, yes, dBRC by d phi. And then the next term involves E phi cross E phi. That is conveniently 0 plus 0. Yes, that's it, right? So we get one term, yeah, you will go back. So now I can add it here, right? I get minus EZC. So I'm getting one more term for EZC, much as we used to get it for the Cartesian. RC, dBRC by d phi. Right, so I've got that. So now the next term, cross d phi E phi, right? So that will be same procedure. E phi, right? So he's made it easy for me. So dB phi by d phi E phi, right? Plus dE phi by d phi times d phi. Right? So this term is not going to contribute now because E phi cross E phi is 0, but dE phi by d phi is minus ERC, and that certainly will contribute. So I have E phi cross product with ERC, that is minus EZC, and then I have a minus plus so that would be plus EZC d phi by, we get now another term for EZC, so that would be d phi by RC, positive, right? So I get another term here plus EZC d phi by RC. Hopefully the third one would not be that difficult, and I can write possibly by inspection. So we have still not done, there's still E phi by RC cross or d by E phi cross EZC, right? So here I'm going to get only one term, right? And that would involve E phi cross EZC, right? So that is simply ERC, right? Which is 1 over RC dBZC by d phi ERC. So leave it as it is, right? Now for the last one, hopefully that would be very easy to write down by inspection, because I'm going to consider only the derivative of the velocity components and then consider the cross product. The first one is EZC crosses with ERC, that would be E phi. So the first term I will get is E phi dBRC by EZC, right? Plus EZC cross with E phi, right? That would be minus ERC. So that would be minus ERC. The derivative there is dE phi by EZC. The last one will involve a cross product of EZC with itself, and that is 0 by the rule of the vector product of two vectors. So this is all I'm going to get. So I can combine this. So it's a vector, so I have to write all the three components. So I can gather all the components of ERC right? So I have d1 over RC dvzc by d phi minus, right, dv phi by dz. So you see it's very similar in appearance to what we had for the Cartesian coordinate. If you look at the Cartesian coordinates, the first component would involve dv3 by dx2 minus dv2 by dx3 and so on. It's very similar to that. Because you're getting, once you take the component ERC, this is the effect of the cross product. You're having dvzc by d5 minus dv phi by dzc. But however, whenever the derivative with respect to phi comes, you see that the dimensional homogeneity requires that, I mean, it's a way of remembering, easy way of remembering the formula, right? So this has to come, 1 over RC has to come. For E phi, clearly, what you will get is E phi, when you look at the positive term, is dvRC by dzc minus dvzc by drc. That's very straightforward, right? And then plus ezc. Here, though, we get an extra term which we could not probably have predicted, right? With these kinds of rules. So then there I have ezc. So I have dv phi by drc, right? Minus 1 over RC dvRC by, but that's not all. I'm getting an additional term d phi by RC. Just as in the divergence, we got this additional term drc by RC, which is somewhat unusual when you compare it to the rectilinear coordinates. Here also we are getting these kinds of terms will appear here and there whenever you are going to these curvilinear coordinates, right? So that sort of completes the formula. You can compare it with what is there in the books, because I just want to make sure that I haven't made any mistake in any of the signs. It looks okay. We have that, right? So that is the curve of a vector. Next we come to the gradient of a vector, which is now going to give a tensor. We've seen all kinds of operations. The procedure is the same. So now what I am having is not the dot product or the cross product. The tensor product is in some books written like this. For us it's simply going to be this. Right? So vector operating on a vector without any sign in between. This is somewhat like AB, or here it is effectively the gradient of the vector that I consider. So how would we handle this? The procedure is the same, right? Earlier, for instance, let's take just the first term. I have this. So this is a vector. It's waiting to operate on what is going to come out of that. It will also be a vector. So together it will form a tensor product of two vectors and give rise to one component of the total tensor. So the way to operate this, again I notice here, the d by drc is going to be very simple to, I don't get an additional term, right? So here, clearly what I have is ERC and then dV by dVRC by ERC and then ERC. All this means is that this is the tensor ERC with the coefficient dVRC by dRC, which will be the component along that tensor. Here though, very important to note the order of the tensor should be, listen, this is the cross product, you have to be careful. Whether it's ERC cross EZC or ERC cross EZC cross ERC. Here, I have the ERC up front, right? So now let us look at the other terms. This acting on this, plus this acting on this. Clearly, you can see that they are all going to give the components along the ERC E5 and the ERC EZC, right? So then I can then add those terms, right? Coming out of this would be ERC EP5 by ERC ERC E5. It's important to retain the order of the terms because ERC E5 is not equal to E5 ERC plus EZC by ERC ERC. So we're getting the components effectively of, because the tensor here is like this, RC5ZC, RC5ZC. So what we are getting here is the first row. So RC corresponds to this, RC5 corresponds to this, RCZC corresponds to this. But we cannot be sure, we are not going to get any more of the components for these tensors, right, from other terms. So that could also happen, as in fact has happened in earlier cases. So let's now look at the next one, which would be the most crucial. And let's look at this. Right? So this is very easy to do because there's nothing to consider. This is actually a tensor product, right? But by a notation it looks like it is multiplying by the vector. This would be component of the tensor, right? So this would be again retain E5 by RC, and then I have dV5 by E5 E5 plus V5 E5 by E5, that is minus ERC. What I said was not quite correct. We may not get any terms on the first row, but here you can clearly see we are getting a direct term E5 ERC from here. We are going to get another term from E5 ERC from this, right? So this is 1 over RC E5 E5. Okay, we are getting another term from E5 E5, and then we are getting minus E5 by RC E5 ERC. The next one would be quite easy to implement because EZC is independent of ZC. So what are we going to get? So I can get from the I'm sorry, this operates on EZC, right? I'm sorry, E by E5 is going to give me component E5 EZC, and that would be multiplied by 1 over RC dBzc by d phi. Right? So far we haven't got any terms. So you're getting two terms here by e phi, you are saying two terms by e phi, e phi. So we have to look at the last set of operations. Clearly, that is going to give three terms, right? One involving EZC, ERC. So maybe I can have to write it out. Times dBRC by dZC plus EZC E phi times dB phi by dZC plus EZC times dBZC by dZC. So all of these will go into the last flow, right? So I can now fill in the components. We're running out of time, right? Unfortunately, I erased the earlier one, but you can easily infer, right, that would be dBRC by dRC, right? And then the next one would be dB phi by dRC. The last one would be dBZC by dRC. Similarly, the last term that we have here would be dBRC by dZC, and then dB phi by dZ. Those are very easy to write out. But then when you come to the middle flow, right, so that is where you have to be careful. So for E phi ERC, I'm getting two terms. So one would be 1 over RC dBRC by d phi, right? And then I have, looks like minus. I hope I've done the sign correctly. But anyway, you can check it with the results in the standard textbooks. And so for E phi, again I'm getting two terms. One would be 1 over RC dB phi by d phi, right? And then here I seem to have a plus ERC by RC. And finally, for E phi EZC, right, that is here 1 over RC dBZC by d phi. Right, so that completes the calculus. It probably turned out to be somewhat simpler than the others even. But you have to be here careful that we are talking about something that finally leads to a tensor. Are there any questions? If not, I think we are done. We've already exceeded our 10 piece. If you have any further questions, you can stay back, others can leave. I'm just going to check if what I've written here is correct and then leave. Please don't wait for me to